Hello and welcome to the CMake presentation at Qt World. I'm going to talk about modern CMake for Qt developers and give you a little history about CMake, and we'll get started right now. So first I'm going to tell you who's this Bill Hoffman guy, and then I'll give the CMake origin story and some of the visions I had for creating CMake way back when. And I'll talk about how CMake's become the de facto standard build system for C++. And then I'll talk a little bit about Kitware, the company I helped found, and how it's going to support CMake and how it supports other open source software. And I'll go into CMake's long history with Qt, starting with KDE adopting CMake in 2006, and both Qt 5 and Qt 6 using CMake. CMake certainly has changed a lot since KDE adopted it. And I'll talk about some of the new features in CMake and some features maybe you haven't heard of. All right, as I said, I'm Bill Hoffman. Hello, I'm one of the founders for Kitware Incorporated, which started in 1998. I'm the originator of the CMake project. And when I'm not running Kitware or doing things for Kitware or doing things for CMake, I can usually be found running around in the mountains. That's a picture of me running a 100-mile race in Washington State this August. Let's start with the CMake origin story. From its humble beginnings on the left of the very first CMake list file, which obviously has changed quite a bit, and how it's become sort of a de facto standard, and you can see right there, there's one of our dedicated contributors and promoters of CMake dressed up as Captain CMake. So where did CMake come from? Well, Kitware was one of 3 commercial companies and the lead engineer team for the Insight Segmentation and Registration Toolkit. This was funded by the National Library of Medicine and was a follow-on to the Visible Human Project. The Visible Human Project created data, CT, MR, and slice data, in that they took a body donated to science, and after they died, they did the CT and the MR, but then they froze them solid and sliced them as thin as they could, taking pictures along the way. And this data set was great for researchers. Imagine you're writing an algorithm that segments the heart out of a CT scan. How do you know you got it right? Well, you can't usually cut the patient in half and see, but in this case, you can. So with the data set out, the folks at NIH realized that really what they needed was the code as well. Not just the data, but the code. And they wanted to create a toolkit in C++. And Kitware was part of that team, and we were basically tasked with making sure that ITK could build on Windows, Unix, and Mac. We weren't exactly tasked with creating a build system, but that's what we did. And I saw a great presentation many years ago by David Abrams at BoostCon. And he showed a slide, and it had Java with hundreds of built-in classes, and Python with lots of built-in classes, and C++ had IOStream. So you can print stuff to the output with C++. Obviously, a lot has changed since then, but one of the things that fostered that change was the open source Boost library. And it aimed to give C++ a set of useful libraries like these other languages have. And what CMake does is it aims to give C++ compile time portability. We can't compile it once and run it everywhere, like Java or Python or C#, but we should be able to take the same input file, declare how we want things built, and then have that work across all the platforms that our code works on. The other thing we want to do is make sure that we can mix both large and small libraries. Remember, this came out of the Insight Toolkit. which was a C++ library for doing research on medical imagery. And we wanted to have the researchers, the students, be able to use this library and build on top of it. So they needed to have their small bit of code link against the much larger ITK library and have that work seamlessly across the platforms they were working on. Everything from supercomputers to gaming machines to laptops to cell phones. Anywhere you find C++, this build system had to work. And that's what CMake aimed to do. The vision I had for the project was that it would only depend on a C++ compiler. Because if you're building C++, you're going to have a C++ compiler. And that it would work on any OS, compiler, or development IDE that supports C++. And as I mentioned before, it would allow the linking of large and small projects, and large projects, basically being able to link together lots of different C++ programs. And this, although is commonplace today and maybe somewhat still difficult, CMake makes it a lot easier, and it was basically a custom solution when CMake was created back then. You had to, basically for each platform, you had to go in and specifically figure out how to craft your application and get it to work with all the different tools and libraries it was using. CMake has changed that. And it supports many build tools, all different versions of Visual Studio, many different versions of Make on different platforms, Ninja, and the Ninja build tool. And that's one of the great stories, I think, of CMake's compatibility. Google came out with the Ninja build tool so they could build Chrome faster. And it did a great job and does really good job with Parallel, much better than GNU Make did at the time. But CMake was able to adopt it and get it incorporated, I think within 2 weeks of it being released from Google. We had at least a preliminary version of a Ninja generator. And what this meant was that anybody that was using CMake suddenly had access to this great command line parallel build tool because they got it through CMake. We support Xcode and lots of different IDEs. And I asked around at Kitware just to see what people were doing, to see what this vision looks like today in the modern days of 2021. So I got a VS Code with TWX CMake plugin, CLion plus tmux and bash, CMake GUI plus Notepad++, Visual Studio and Visual Studio Code, Kdevelop on Linux. But some, of course, like Trinity, prefer the command line. I'm pretty sure Trinity had to run CMake to hack into that system. They just didn't show that. That got cut out of the movie. One of the developers, Kitware, uses NeoVim, ZShell, and tmux. He wasn't so sure a screenshot would look very good, but basically that's what you've got. Running CMake cross-platform and letting the projects take advantage of the most precious resource, which is the developers. And each developer has tools and environments that they're most productive in. And CMake allows these tools and environments to be used even on the same project. You can have people working on different platforms. You can have people working on the same platform with different IDEs or different command lines. Myself personally, I like Emacs and the command line, Emacs with Ninja. In running CMake, there's a CMake GUI, which is built on top of Qt, of course. CMake, which is a terminal command line interface, and then CMake's non-interactive command line. The CMake workflow shown here, you run CMake, give it a source directory, it does the configuration, then you can type CMake ---- build with a J flag, tell it how much to build. Now I touch the CMake list file, I type build again, and it reran CMake, reconfigured the project, rebuilds, and then I can run all the tests. So that leads you to this slide, which shows a flow chart of what happens when you run CMake. The first thing CMake does, if there is one, if it's been run before, is read the CMake cache file. Now this cache file is a way of storing the environment for that build. Prior to CMake, on a lot of projects I worked with GNU-make and AutoTools, a lot of times the project would require setting a handful of environment variables to point to where things are in your local system. And if you got those environment variables wrong or forgot to set them, and then you typed make, everything could go haywire. And files could be written all over your disk by mistake, and it was a big mess. And I wanted to make sure that CMake didn't follow that same pattern. But we needed a way to store that information that CMake discovered about the system, or even that particular build. Because remember, CMake can have a source directory with multiple build directories pointing to it, built-in out-of-source builds. And each one of those has the cache file with the specifications of that build stored in that cache file. And the way it works, it reads that, and then if you need to make any changes to those, like user options, those can be displayed to the user through the GUI, and you could change them. And if you need more edit, you can run configure again, and you can keep cycling through. When you're finally ready, you can hit generate, and this generates that build system, that native build system. And then you can run the native build tool, or CMake ---- build. And from then on, you don't need to run CMake itself again. Once you've set up the system and built it once, then CMake will know how to keep itself up to date. If any of the inputs to CMake are changed in the future, it'll know to rerun CMake automatically for you. And the developer can move into that world that they're very comfortable with. Now let's take a look at CMake becoming the de facto standard. Now this is a talk from Bryce Adelson at C++ Now, and we'll just sit back and listen to what he has to say about CMake.
CMake has over 50% market share. Every toolchain, IDE, and package manager supports it. You want a standard C++ build system? You got one. It's called CMake. Resistance is futile. Just use CMake.
Thanks, Bryce, for the kind words about CMake. Or maybe not so kind, resistance is futile. I guess we're the Borg taking over the world. But the point is, CMake has grown in popularity. And one of the things I wanted to show you, JetBrains creates an IDE, and then they do a survey every year. And CMake went up from 42% to 53%. And you can see Visual Studio under there has a high percentage as well, and that also ships with CMake. And we're seeing lots of job openings with companies like Tesla and MindSource, LinkedIn, Samsung, Apple, Microsoft. Usually there's 400 or 500 job openings that require some usage of CMake. So with that, I'd like to move into talking about Kitware and how we plan on supporting this. So, we've created this tool, with the support of the community, and built it up, and it's become this standard. How do you know it's going to keep going forward? Well, I'm going to talk a little bit about Kitware. So we were founded in 1998. Our focus is on science and technology, not creating IP or selling software. And our emphasis is on collaboration and open science. We have an HPC visualization group, a medical computing group, computer vision group, a data analytics group, and a software process group that works with CMake and other software process tools. The scientific group does some really great stuff, from physical-based rendering to end-to-end simulation workflows, tomographic reconstruction, LiDAR visualization, high-performance computing. Our medical computing does medical visualization, image-guided intervention and surgical planning, computational physiological modeling, digital pathology, dental image analysis, virtual surgical simulation and training, working with ultrasound images. Our computer vision group is very adept at deep learning. They can do object detection and tracking, image and video scene understanding, image and video forensics, finding fake imagery, social media analysis, complex activity and event threat detection, super resolution from video, and 3D model construction from video. Our data analytics group can do advanced software metrics, geospatial analysis, bioinformatics, and large-scale imagery, visual data science. And then the software process group works on building software processes and supporting CMake as part of our group, part of what the group does. And how do we do that? Well, we have our government and commercial, government labs, grants, commercial and university prime contractors, commercial and university subcontractors going through our Kitware contracts and finance. And then that's able to pull together Kitware experts, customer collaborators, community users, and community developers into an ecosystem of open source platforms such as VTK, CMake, ITK, and PeerReview. And along the way, we've had some unlikely but way cool contributors. I think one of the fun projects, we've worked with the Minecraft group at Microsoft, formerly Mojang, to help them with their CMake build. And what they've done has been contributed back into the open source CMake. So by building a larger community, bringing in new people, every time a new person adopts CMake, we get new features and it grows. The Minecraft, of particular note, they gave to the community CMake presets and CMake user presets.json. I'll talk about that a little bit later. Visual Studio has been sort of amazing for me that they've incorporated it and embraced CMake, in that CMake is actually shipped with every copy of Visual Studio, along with the command line Ninja build tool, because it is so fast and efficient. And I always sort of kid that, early on when I wrote CMake, I had to completely reverse engineer the Visual Studio project files. And I'm pretty sure if Microsoft knew what I was doing, they would have sued me and sent me a cease and desist order. But fast forward 15 years, and they're collaborating with me and working with Kitware to actually develop features in CMake that they can then put into their product. So that's a real big win for the community and for all of C++. But obviously, Kitware and myself can't take all the credit for CMake. It's a massive community effort with almost 1,000 contributors, according to GitHub, and authors of books that are on CMake that developers can use to learn CMake, and a thriving community with CMake discourse running from Kitware servers. And it's just been great to take part in that huge community effort. CMake is also able to adapt to new technologies quickly because of its open source model and Kitware's dedication to the product. New IDEs and compilers, as soon as Visual Studio releases support, comes out with a beta, we've got support for it in a few weeks. Xcode releases supported weeks after the beta comes out. And Ninja, I already told the story of that, the command line build tool from Google, that has continued to be supported in CMake. Also, when Apple Silicon came out, Apple reached out to Kitware, and Kitware worked hard to make sure that CMake would work and that projects built using CMake would seamlessly work on this new architecture. When new compilers come out, whether it be Clang or GCC versions or Visual Studio versions, CMake community and CMake developers stay on top of that and make sure that CMake supports them as soon as possible. And what makes CMake so popular? How did it become a standard? I like to think it's because it actually does a lot with a little bit of code. So if you look here, we've got add library, add executable, and add test. Those seem like small commands, and they are, but a lot's happening behind those simple commands. There's shared libraries getting created, static libraries, many compilers and IDEs are supported, and there's just a lot of things going on behind the scenes that allow developers to have access to this wide range of C++ ecosystem. Qt is the de facto standard C++ framework for high-performance cross-platform software development. And in fact, we use it at Kitware for CMake itself and for our peer review project. So I think Qt and CMake have a lot in common, and I'm really excited that Qt adopted CMake as its build system for Qt 6. But CMake goes back a long way. We have a long history with the Qt project. And it really starts in around 2006 when KDE adopted CMake. And you can see here, this is the Google search trends. And right around when KDE adopted it, you can see that blue line sort of rising up, and there's a lot more interest in CMake, and AutoTools starts to drift off. There's a great article, if you're really interested in how KDE switched to CMake, that Alex Nurendorf wrote. But basically, the highlights of this were that at the Academy conference, Alex wasn't able to attend, and the scones contingent, scones is another build tool, actually won at the conference, and it was decided that KDE would build with scones. And Alex gave me the bad news after the conference was over. And you win some, you lose some. But then like 6 months later, Alex sent me an email and said, I think we have another shot. Look at this. And on their email list for KDE, the build list, someone said, look, we've been going at this scones stuff for like 6 months, and I can't even build KDE base libs. Maybe it's time to look at something else. So Alex told me this, and I said, fantastic. And we kind of dropped what we were doing at Kitware, at least I did, and we focused on getting KDE built with CMake. And within a week or two, we had KDE base libs working. And they have sort of a rule in KDE that he who codes wins or decides. And that's exactly what happened here. We were able to get something going really quick, and it worked pretty well. And then someone was able to get it working on the Mac, and then Windows shortly followed after that to allow KDE applications to work on Windows as well as Linux. But of course, CMake wasn't perfect. It still isn't perfect today, that's for sure. But we were able to change and adapt as we were integrated into this new community of great developers from KDE. One of the first things they complained about was that install used to take a really long time because to reset the RPaths, it would relink all the executables and libraries. We ended up writing a ELF editor and integrating that into CMake so that CMake could rewrite that without linking, and it became much faster. We had to add proper shared library versioning with the full symlinks on Linux. In the past, we just sort of spit out a .so file, and that was the end of it. But obviously, that wasn't something that was useful for production work that KDE was doing. Many Find modules were added by KDE. The Find package handled standard args was contributed by Alexander. Package config support was originally started as part of the work we did for KDE. And in 2018, Qt switched to going to CMake. They deprecated their QBS build system that they were working on and went with CMake as it continued to grow as a de facto standard. So Qt and CMake, past, present, and future, was a blog put out by the Qt company. And just like with KDE, there were deficiencies in CMake that had to be addressed in order to build Qt more effectively. And Kitware worked with the Qt company and with a lot of open source developers to add some new features. Let's take a look at that. We've added precompiled header support, Unity build support, dep file support for automoc and Ninja, add custom command dep file support for Makefiles, Ninja, and Visual Studio, Ninja multi-config generator, iOS multi-architecture builds, a file configure command, an eval, a way of evaling CMake code within CMake, a call me later or deferred code in CMake, and properties on source files for different directory scopes. And of course, there's more to come. Let's take a look at Unity builds. Let's take a look at Unity builds. What's a Unity build? Essentially, this combines source files into batches and then sends them to the compiler all at once so that it compiles lots of files at the same time instead of doing them one at a time. And this has certain efficiencies for cache location and pound includes. And this makes the code build faster. So you can compile these Unity sources instead of the originals. This is supported since CMake 3.16. So with a global flag, CMake Unity build on, you can turn on this CMake. So you can see in this little video here, CMake -d Unity build on. And then you type Ninja, and it builds the source files. And then if I turn it off, you can see it building the source files individually instead of as a batch. You can set the batch size with Unity builds, controlling the grouping size. You can set the Unity build mode, batch or group. So you can set up different groups that are built. Precompiled headers were also added, so you can see sort of a trend here to try to make things go faster. From Unity builds to precompiled headers are all meant to speed up compilation. Precompiled headers create partially processed header files, and they're used when compiling instead of repeatedly parsing the same .h files over and over again. And this again was introduced in CMake 3.1.6. To set up precompiled headers, you would create a library like this, and then set the target precompiled headers on that library, and give it the name of the interface, leaf.h in this case, which would be the file you would include to get the precompiled headers. And all of this gets generated for you and is built into the CMake project. One of the other features we've added since Qt adopted CMake is add custom command can now integrate custom dep files or .d files that have dependencies. So if you're writing your own domain-specific language and it has some sort of pound include system, you can express those dependencies in your custom commands by generating a .d file. And we now support this in all of our generators. Another thing that's changed a lot since CMake was originally adopted by KDE is modern CMake. And what does this mean? This essentially means that the target, and in CMake a target is either a library or an executable, these targets contain all the information that are required to compile them. So like include flags, preprocessor flags, -d flags, compiler flags. Anything you need to use or to build that is specified on the target. And then when someone links to that target, those flags and options are all transitively passed to any of the consumers of that target. And this means that the directory layout really is independent of what the flags are, which wasn't something CMake used to be able to do. It was very tied to the directory structure and sort of that directory inheritance, and that's how the flags worked in the past. But now your executables and libraries can be wherever they need to be, and they express what they need to use those libraries. The usage requirements, this is done through private, interface, and public requirements. So a private interface is something that's only given to the target when that target's being built. An interface, only consuming targets will use it. And you can look at the build interface, and that's used by consumers from this project. or out of that build directory. So when you're building a tool, inside that build directory, you've got certain flags you might want to use. But then once you've done make install, and the target is now completely separate from the build system and it's already been built, then you might have a slightly different interface. The -i flags might be different based on how you install your header files. Or you might have different -d flags. So there's a way of specifying those two different interfaces in the usage requirements. CMake find modules went through a big revamp so that they too can follow this pattern. So if I do find package PNG required, then I do add library trunk, shared trunk, and then I do target link libraries, private PNG:PNG. This is no different than if I built PNG in my project, or if it's something I found on disk that's already been built. I'm just saying that I want to link to PNG, and CMake needs to know what flags and options to use to do that. CMake provides over 150 find modules. You can list them all with CMake -- help module list, or look at the documentation online. Presets, this is a relatively new feature in CMake, and it allows for common configuration flags, variables, build directory, generator, etc., for a project to be stored in a JSON file for reuse. And it's got two flavors of the file, CMake presets.json, and this one is meant to be version controlled for sharing between users and systems, and CMake users.preset.json. This is not meant to be version controlled, and it's for storing local machine-specific or very user-specific information to pass to CMake. So let's look at a simple example here. Here's a JSON file that configures, it's a configuration preset, and its name is Ninja Debug. And I'm saying I want the CMake generator to be Ninja. So when CMake generates, the backend I want to use is the Ninja generator. And instead of telling what binary directory that you normally have to do when you run CMake, I want the binary directory to be a subdirectory of my source directory called build/debug. And then I want the cache variable CMake build type to be initialized to debug. And then when I go into my nice CMake GUI built with Qt, I can select Ninja Debug and hit generate, and I will get a Ninja tree that's pre-configured, all set up for build type debug underneath my source directory in the build debug directory. Another new feature of CMake is that CMake now has real color. So you can see the reds, yellows, and blues in there when you're running CMake. So I've alluded to this, but CMake also has, and I think it's one of the pretty powerful features, a full cross-platform install system. You can specify these rules to run an install time. You can install targets, files, and directories, and provide default install locations. Something we're working on that's very close to being done is there's a file get runtime dependencies, and we're integrating that with install targets. And what this allows you to do is, let's say you're writing some big application like ParaView, let's say. That's a Qt application, and it links to all the Qt libraries and maybe links to another half a dozen other libraries on the system. And I want to package it all up in one installer and be able to package it. I can call this file get runtime dependencies, and it will use LDD or depends or OTool on Mac. Basically, it'll use whatever the platform needs it to use to figure out what shared libraries that executable links to. And then it will collect them all and put them in the install directory next to the executable or where you want them. So this allows you to do very nice packaging of large systems. Speaking of packaging, CMake has what's called CPack. And to me, packaging, at least before CMake had it, was somewhat of a dark art. I always like to tell the story. With the original version of CMake on Windows, there was one guy at Kitware that knew how to run the packager that would create the installer. And there was one computer at Kitware that had the installer software on it. And if that computer was down or Ken Martin wasn't in the office, there wasn't going to be a Windows release of CMake. Enter CPack. CPack is now bundled with CMake, and it can create professional platform-specific installers. It supports Unix tar.gz files, Windows Wix or MIS installers, Nullsoft install system, Mac OS X drop and drag or package maker, Debian packages, RPM package manager. And essentially, again, you can outsource that packaging to the CMake developers and use CPack to create installers for your project, even if you don't know how those installers necessarily work. For using CPack, what you really need to do is on Windows, have an install command, zip program, NIS or Wix, and the whole gist of getting CPack to work is getting install to work. So you set up your install rules and maybe use the install with get dependencies that we just talked about. And then you make sure your executables can work with relative paths to where they're installed. And they can work, basically it needs to be relocatable because an installer is just going to package all that up and install it somewhere on someone's computer. So everything needs to be relative to that. But once you get those install rules and get your software working so that it can run from anywhere, relative to a certain directory structure, then you set a few CPack option variables, if you need them, and include CPack. And then suddenly you're able to create these installers on many platforms. CMake also includes testing. Testing needs to be enabled before you can use add test by either including ctest or calling enable testing. And the executables that you pass to the test should return 0 for passing. And ctest is an executable that's distributed with CMake that allows you to run these tests in a project. To run them, so in this example, I've done my build, and I just typed ctest. And you can see it ran a couple tests and showed me they passed and how long it took to run them. You can give some options to ctest. It supports running tests in parallel with a -J option. -R lets you give a regular expression to be able to choose tests. You can specify the verbosity level. You can tell it to rerun only the failed tests, which is very useful when you're debugging your code. And for more information, you can do ctest --help. We've also integrated Google Test and have a gtest discover test. And this allows those Google tests to be discovered after the executable has been linked. Then before ctest is run, it can query those executables and put it in ctest files so that it knows how to run those tests properly. Another project that CMake has as part of this software process is C-. It's a LAMP stack visualization application that allows you to see configuration warnings and errors, build warning and errors, tests passing and failing. You can even do dynamic analysis like address sanitizer or things like Valgrind. And another thing we do, this is a cool project we did at CMake, is we have our own hosted GitLab CI, and we have a Redis server, which is a Linux machine with a ton of memory, and we run SC cache integrated into our CI builds with CMake Lang compiler launcher. And essentially, this allows object files to be reused. And it doesn't even need to fetch them off disk. It's got them in memory on the Redis server. And if the exact same compile comes up, it can just grab that using hashes on the content of the preprocessed source files. So that gives us this great software development environment where coders write their code, they check it in, it's tested, there's this dashboard they can look at. And this whole process is something we've been doing at Kitware for the past 20 years and refining it. One more feature that we're looking to add to CMake is C++ modules. So in the future, C++ will have modules. So let's look at this simple example. We've got hello world, which exports module hello world. And then I've got a main that imports hello world. Now, if I do this, suddenly now I can't compile main before hello world, because hello world needs to be compiled to that module interface. So that is a problem. What are we going to do? Wait a minute, CMake's been doing this for 16 years with modules and Fortran. We added support for this into Ninja in 2015 so that you can dynamically change the build graph in Ninja as those dependencies are discovered. Essentially, with each source file, you need to know what it produces and what it uses. And you need to build that graph and then build the files in the right order. And all those changes that we made for Fortran are now merged into Ninja because of the impending C++ modules. So what's the best way to learn CMake, I'm often asked? Copy someone's CMake code from 2010? No, that's obviously the wrong way to do it. There's a lot of bad CMake code because CMake's been evolving so much. Watch a talk on modern CMake. There's a lot of them. Get Professional CMake by Craig Scott. Join our discourse forum. Look at the online documentation. Go through the tutorial. Go through the new guides. And these guides are tested code. We've created a way of having the markup language refer to the code that actually gets tested. And then this gets generated into the documentation. And Mastering CMake, the book that Kitware used to sell, is now open source. You can help contribute to that book. We're working on having a printed copy again. And then, one last sort of story I like to tell is, remember the ITK project, the Insight project? It's got a very complicated wrapping system that involves parsing the C++, running Swig, doing all kinds of complicated stuff. And CMake allows this to be pretty seamless. And I hadn't looked at it in a few years because mostly I'm at Kitware doing pointy-haired boss stuff. But now, I had to take a look at this, and I installed Visual Studio, Git, and Python. I cloned ITK, ran CMake with wrap Python on, typed Ninja, and everything worked flawlessly. And I got a Python-wrapped ITK. And during the build, CastXML was downloaded, PyGCXML was downloaded, Swig was downloaded, and all of these were used to build this complicated build process, and it just worked, which is really sort of the vision I had for CMake from the beginning, that complicated things like this could be made easy. So thank you for listening. If you want to talk to me, you can email me at bill.hoffman@kitware.com. You can read how to write a CMake build system on the CMake documentation page, or explore the documentation. And I hope you have a great Qt World Conference. Thank you.